This topic is on enzyme kinetics, and enzyme kinetics can be an entire course in and of itself. We're just going to highlight basic features of how enzyme catalyzes a reaction and how an enzyme time course measurement can be used to get kinetic parameters that define that enzyme. In our case, we're going to be looking at single substrate enzymes and keeping it as basic as possible, but we'll also kind of show you some of the more complex situations that can arise for most enzymes because typically they use two substrates. The learning objectives are described below. So when we look at the general properties of an enzyme, we're talking about a folded protein. It could be a monomer, it could be a dimer, it could be a hexamer, it could be very complex. It just depends on the enzyme. And the purpose of the enzyme is to increase the rate of a chemical reaction. And they do so by factors that range from 10 to the third to 10 to the 20th. So we're talking about huge rate enhancements. So these reactions occur under 37 degrees Celsius and room temperature, 1 atmospheric pressure. We don't have to go to extreme conditions in order for the reactions to occur. And they occur with great stereospecificity and regioselectivity as well. So these reactions are very efficient because of the design of the enzyme's active site. And so we'll be talking about mechanism in another topic, but right now we're just going to focus on how do these enzymes catalyze reactions. So I already mentioned the fact that these reactions occur at physiological conditions. It's important to note also in terms of free energy, an enzyme will not induce a reaction that is unfavorable. So you have to provide conditions that are favorable. So sometimes based on the conditions, the reaction is favorable in one direction, not another. So based on chemical principles, any chemical reaction is microscopically reversible. However, it has to have conditions to do so. And so often enzymes make catalyzed reactions experimentally. If we do isolate an enzyme and try to characterize it in the laboratory, it may go in one direction, but in the cell, it may be favored to go in the opposite direction. Often in the laboratory, we'll alter the direction of the reaction simply because it's easier to study it in the other direction. But we have to provide conditions that actually can occur. And some enzymes can actually go both ways depending on the cellular or conditions. So just keep that in mind. Have high specificity. You're not going to get side reactions. For example, like when you do chemical synthesis, sometimes you get byproducts, or you get racemic mixtures where you have mixtures of different enantiomers in the reaction, or you'll get diastereomeric pairs and things like that. We don't have that problem here with enzyme catalyzed reactions. They're very stereospecific. Now, they sometimes do have a different ability to bind substrates, and so sometimes you can have a different product depending on the substrate that's bound, and we'll talk about examples of that throughout the course, but they are very specific for the substrates that are that the enzyme's designed to bind and to react with. The enzyme itself is unchanged in the reaction. That's the definition of a catalyst. It accelerates a chemical reaction, but in itself is unchanged. Now, it may be modified in the process of the chemical reaction, but at the end, it eventually gets converted back to its original form and ready to go through another round of catalysis. The key hallmark here of enzymes are that they're subject to regulation, and this will alter their ability to bind substrates or to catalyze the reaction. So this is how we can control metabolic flux, is by these regulation of the enzyme through allosteric regulators. So we'll talk about that. That's the key thing about enzymes, is that we can regulate their activity and promote whether they're going to be inhibited or activated. The largest class of enzymes are protein-based, and so that's what we're going to focus on in this course and these topics of enzyme kinetics and mechanisms. But it should be noted that the RNA can fold into complex structures, and you'll learn about that in one of the other topics in this course, and that there's actually catalytic RNA molecules called ribozymes that catalyze chemical reactions. So what I want to go through next are how enzymes are classified. So the classification is a way to categorize the enzymes and to put them into different specific families or categories based on the chemical reactions that they catalyzed. And this was done by the International Union of Biochemistry. That way we have a systematic naming approach, and you have what's called this enzyme commission number, EC number. So if you were to order, say, an enzyme from a biochemical manufacturer, it will give you the name of the enzyme, but it'll also give you the commission number. And each number represents, the first number would be the protein class that I'm going to go through with you here. There are 6 of them. And then there's subcategories as well. And so I just wanted you to be aware of that. We're not going to have you memorize these enzyme commission numbers, but just be aware if you do see that, if you're working in a lab, it's like, oh, I know what that refers to. It's how it's classified. So the first category we're going to look at, first classification, are the oxioreductases, and these are enzymes that catalyze oxidation reduction reactions. Remember, redox reactions. These are the ones in which electrons are transferred. So don't forget, you have to be able to recognize this type of reaction, and this will be through this mnemonic device oil rig. Remember, oxidation is loss of electrons and reduction is gain of electrons. Now, a proton usually is also involved, because if you gain an electron, it's negative, and so if you gain a proton along with it at the time, it's positive, so you don't have a change in the overall charge in terms of the transfer process, because you'll do a negative electron and a positive proton, and it kind of cancels each other out. But it depends on the chemical reaction in terms of what is happening there. So you should refresh your memory of oxidation reduction reactions, where you have one molecule that's reduced, the other one's oxidized, and the transfer of electrons from the reduced to the oxidized version. The reduced substrate becomes oxidized, and the oxidized substrate becomes a reduced product. An example is shown here. NADH is an important cofactor that's involved in oxidation reduction reactions. You may recall the use of this oxidizing agent in some of our redox reactions, where we were calculating delta E0, delta E0 prime values to see if a reaction was spontaneous or not. And so we'll actually talk in more detail about the chemistry of these types of oxidizing agents, cofactors, in the cofactor topic. So I do not want to belabor that here. But notice the role of this oxidizing agent is that you have a alcohol, and it gets oxidized to a carbonyl group. So if you were to calculate the oxidation number on this carbon, you would see the number change accordingly. And so you have a good idea of the flow of electrons from the alcohol to the oxidizing agent to form NADH. So we'll talk more about the detailed chemistries of these types of electron transfer reactions of these cofactors in the cofactor section. But right now, just remember the first class is oxioreductases. The second class is a transferase, and so the general concept here is you have a substrate with a moiety, a functional group, or some part of the molecule that you like to transfer it to B, and then B accepts that group, and then ASD doesn't have it anymore, and so this is called a transferase reaction. So you can't transfer a chemical group from one molecule to the other. And here's an example here of alanine transaminase, where you're basically taking the amino group. This should be positively charged here. It's missing the positive charge on that, and it's transferred over from alanine or to alpha ketoglutarate to generate glutamate. So we'll see this reaction later in the course. Hydrolases, we talked about ATP hydrolysis in regards to some free energy calculations and looking at and how to couple group transfer reactions to unfavorable reactions through ATP hydrolysis. So this is more of a general formula for hydrolysis reaction shown here, where you have A and B, and you're going to hydrolyze the bond connecting A and B, and you generate free A and free B. And so this is a hydrolysis reaction. So the example here would be pyrophosphate, where we're going to break this phosphoanhydride bond through hydrolysis, and this is done through pyrophosphatase, and you generate 2 molecules of phosphate. In this case, this would also, depending on the pH, could be protonated or not. Probably be protonated, at physiological pH. So again, using water to break a chemical bond, hydrolyzing it. And there are a lot of different enzymes that are involved in that. So when we go through different reactions in metabolism, it's helpful to think of them in these classifications. Oh, that's an oxioreductase, or that's a transferase, or that's a hydrolase. And we got 3 more to look at here. The fourth classification are lyases, and this catalyzes the lysis or breakage of a chemical bond. But in this case, water is not involved. So the hydrolases have water involved. These do not. It's not an oxidation reduction reaction, and usually you get a double bond generated in the product. So for example, if we have pyruvate here and we're going to decarboxylate it to form acetaldehyde and carbon dioxide, this is an example of a lyase. Okay? Lyase reaction, where we're breaking a group off of a molecule, but water is not involved. In this case, you see a proton could be required, but there's no water involved in the breaking of the chemical bond. Isomerases are another classification, and there are quite a few of those. And this is to catalyze a structural change in a molecule. It's an isomerization reaction. So for example, we have malate here, and we're going to look at the substituents here that are in the red arrows are carboxylates, and you can see that they are on the same side of that double bond, so they're cis configuration here. And so if we have this isomerase, we can break a chemical bond here between these 2 carbon atoms, and then we're going to rotate that over and then add the carboxylate group back to generate the trans version of this molecule called fumarate. Okay? So there's a change in configuration here. We're taking one group off and putting it back on in a stereospecific way to change the configuration. And so we can have A variety of enzymes will do this. This is showing a double bond change in configuration from cis to trans, but there's other reactions where you can go from, say for example, R to S at a particular carbon atom. We mentioned proline in terms of peptide bonds being either in the cis or trans conformation. Well, there's enzymes that help to isomerize and change the conformation of prolines from cis to trans. And so those are also isomerases as well. So anytime you change a configuration, you have an isomerase. The last category are the ligases or the synthetases. So they usually have the name synthetase if you're making something, putting something together, ligating two molecules to form a new molecule. This is called a ligase or a synthetase. And example of the general structure is shown here in terms of the mechanism, where we have A and B, and usually there's some kind of nucleotide, NTP. It could be usually ATP, but it could be GTP as well. And they usually use this phosphoryl transfer in its mechanism. And so it's kind of like coupling the reactions together, where we talked about that in terms of thermodynamics, where an unfavorable to put A and B together, but with the help of a cofactor, like a nucleotide triphosphate, we can promote the ligation of A and B. And in the process, we end up generating the dinucleotide diphosphate and free phosphate in the reaction. Okay, so we'll show examples of these synthetases or ligases. So you should know the 6 categories and be able to recognize them based on the reaction that we talk about. So we'll mention this as we go through different topics, and especially in metabolism, where we go through the pathways. So it kind of helps you think about what's happening chemically, and sometimes in the name of the enzymes telling you what's happening, and helps you think about the pathway and the substrates and the products as you go along. Here's just a nice table that's in your textbook, and it does the summary of the different classifications and examples, and showing you the enzyme catalyzed reaction. So I showed you some of these. Some of them I showed you were different in the other examples that I provided. But this is a good summary slide to kind of make sure you know what the classes are. And again, I don't want you to memorize specific reactions or enzymes for these categories, but understand more of the general features of each classification. And can you recognize them from given reactions? So how much rate enhancement can an enzyme catalyzed reaction provide? So I like this figure here. This is from a paper by Wolfenden and Schneider almost 20 years ago now, in Accounts in Chemical Research. It's a nice review article in how they determined these rate constants. So what they did, they determined an enzymatic rate constant based on taking the substrates, sticking them into like basically a pipe bomb. They seal a stainless or a tube, and they put the reactants in there, seal up the ends, and heated it up to like a couple thousand degrees. Let it cool off. Did that for a certain period of time. Let it cool off, and then he measured how much was left, and they were able to get some half-lives, rate constants, and so they used that to compare it to enzyme catalyzed reactions, and that's what's shown here. So you can see a reaction that differs between the non-enzymatic rate constant and the value on the bottom of the line. At the top of the line is the enzymatic rate constant. And so what I want to show you is you can see these huge enhancements of the enzyme catalyzed reaction. So the bigger the difference is bigger the enhancement. So let's look at this one here, ADC, arginine decarboxylase. So you know what arginine is. That's your amino acid. And if you're going to decarboxylate that, and if you're going to let that happen, naturally, you're looking at half of the arginine will decarboxylate in, I don't know, maybe 4 billion years. So what happens if you stick an enzyme in there to help decarboxylate it? Well, now you can do, let's see, this is a log scale here. This is 1, 10, 100, 1,000. You get 1,000 events per second. So huge rate enhancement based on an enzyme. And so how do the enzymes do this? Something that you had to put in a pipe bomb and heat it to thousands of degrees Celsius, how, Fahrenheit, depends on the scale you're measuring, how can you, an enzyme, if you will, catalyze such a reaction? To me, that's a very interesting thing. How's it do that? Well, that's what we're going to talk about. We're going to talk about how we measure these rates experimentally and what these rate constants that we obtain from these measurements mean in terms of rate enhancement. And then in different topics, we'll look at mechanism of how the enzyme does it from a chemical perspective, chemical mechanism, in one of the other topics for just one enzyme, chymotrypsin. But right now we're going to look at how do we measure this stuff. So we're going to look at a simple system here, and I'm just going to try to explain key features. You can read the details yourself in the slides. Try to summarize these things in a way that features the key points. And so we have an enzyme E, usually abbreviate the enzyme as E, and substrates as S. In this case, it's E plus S. So it's an enzyme that binds one molecule S, the reactant. And when it binds, it's just like we did binding of myoglobin and oxygen. The substrate has to bind to the active site first. So there's this binding event. And we call this the ES complex, enzyme substrate complex. No chemistry has happened. This is just a binding event. And so it either could associate or dissociate. And so that's what that's showing here. So you have a K1, which is a rate constant in the forward direction, and you have a rate constant in the reverse direction. Usually the forward direction is 1 and reverse direction is -1. We've seen this convention before. And so this is a binding event. So that's the first part. It's a binding event. There's a recognition of the enzyme for the substrate. So the substrates can get quite large, but if we think about arginine in the arginine decarboxylase reaction we mentioned in the previous slide, you can think of parts of the enzyme that would recognize an arginine, right? You have a negative carboxylate, you have a positive amine, and you also have a positive guanidino functional group on the side chain of arginine. And you can see the side chain of arginine is quite long, so you may have this binding pocket that recognizes long side chains of amino acids with a positive charge. And so there's a substrate specificity unique in the folded enzyme's active site, okay, that recognizes substrates very specifically. It's not going to bind other amino acids because they don't have the same side chain. They have other features that are the same, like the negative carboxylate in the protonated amine, but it doesn't have the side chain there. So there's the specificity we talked about, and this is a way to look at it in terms of a binding event, okay? Forward to form the complex or dissociation of the complex. Now let's look at what happens to the substrate complex if it doesn't dissociate. Well, then the chemistry is going to happen. In the enzyme active site, it can either dissociate away to form free enzyme and substrate, or it can help enhance the chemical reaction and form the enzyme and product. So this K2 here is the enzymatic rate constant. This is the chemical step, okay? And based on the property of microscopic reversibility, there's also a K minus 2. If you were to have the product in the enzyme come together, it could go backwards and form the substrate. So enzymes can do this. It just depends on the properties of the enzyme. So often usually enzymes are going to be going more favoring one direction than the other. So your rate constant of the K2, for example, would be larger than the K minus 2. And that's kind of shown here in the size difference in the font as well as the arrow, okay? So this is this process that's going on. The enzyme binds substrate to form a complex, either dissociates away or goes and forms product. And this concentration of ES is being partitioned in two different directions, dissociating away or forming product. So it depends on these rate constants as what's being favored or not. Okay, so this complex is formed, but it's either going to break apart or form the products. All right. And if it goes backwards, it's going to be, you have to have enough of a recognition of the enzyme for the product and be able to catalyze the reverse reaction. So this K minus 2 is usually very small, so it's hard for it to go backwards unless certain cellular conditions help promote that as well. So we can figure it this almost as being just K2 only in most cases, okay? So that's the model that we have. Now let's look at the process of the enzyme catalyzed reaction in terms of thermodynamics. And I mentioned this a little before in the thermodynamic topic, where we talked, or a topic on thermodynamics, where we looked at how free energy can also be related to the activation energy in terms of a delta G double dagger, how a reaction is catalyzed. So let's look at a reaction that is not enzyme catalyzed. So we have a G value for our substrates or reactants, if you will, and a G value for our products. And if we look at the distance between here, that would be our delta G of the reaction. You calculated those for a lot of different problems that you've already worked on. But we also said there's this a delta G double dagger that's related to the activation energy. And so as the reaction proceeds and we form an enzyme substrate complex, that substrate will undergo some chemical reaction that in the active side of the enzyme, and will form a transition state. And that transition state is stabilized by the enzyme. And in the case of a non-enzyme catalyzed reaction, it has to be a thermal transfer of energy due to the association to elevate it to a high enough level to promote the reaction to occur. And that's called the activation energy. So we can enhance a reaction by increasing the number of collisions. You can look at that in terms of statistical dynamic calculations there. If we were to do this in the presence of an enzyme, look what happens. The enzyme's active site helps promote the reaction by orienting the substrate in an active site and providing groups to facilitate the chemical reaction, bringing them together. And so we'll talk more about those processes in detail. But what it does, though, it lowers your transition state energy. And now your delta G double dagger is much smaller, and it helps to promote the reaction because you do not have as big a hill to overcome. So if you have a bigger transition state, more energy is required to overcome it. If you lower that, it's easier to go over. You're promoting the reaction. Notice your delta G of the reaction hasn't changed. So those thermodynamic free energy values you would determine doesn't change overall the reaction. It changes its pathway based on the delta G double dagger of the transition state. The diagram is shown here comparing the uncatalyzed reaction to the catalyzed reaction. So I think it's important to spend a few moments looking at this diagram so you can understand more of the way free energy is involved. So if we look at the reaction coordinate, again, we're looking at some chemical bond being studied over time. And so say it's a ligase and we're breaking a chemical bond, so we can monitor that over time. So here's our substrate here, and our uncatalyzed reactions in blue, all right? And so the delta G of the reaction here is the difference between the free energy of the substrates and the products, and there's your delta G of the reaction. You calculated many of those in different problems. Now if we have a uncatalyzed reaction and we want to calculate the delta S or delta GS of double dagger, this activation energy, it'd be from this position up to here, and that's what we're showing here, uncatalyzed. All right. The catalyzed reaction involves the enzyme binding to the substrate to form the enzyme substrate complex. And so, depending on the property of the enzyme, this can be close to the substrate or it could be even lower in energy. But it'll vary from enzyme to enzyme. But you can imagine it binding the substrate in such a way that it lowers the overall energy because it freezes the substrate from a lot of rotations, and so it's going to keep it in a lower energy state. Then when you do the chemical reaction, you have to go to a delta G double dagger or a delta S double dagger, just like you do in the uncatalyzed reaction, or the S double dagger. And then you form an enzyme substrate complex, product complex. And that enzyme product complex has to dissociate away to form the free product. And then you end up with your free enzyme that can go through another round of catalysis. So let's look at where your delta G value is again for the reaction. Well, that hasn't changed. See, the substrate and product still have the same delta G of the reaction. However, the pathway is different. And so the delta G of the double dagger of the enzyme catalyzed reaction, which we call E sub S here, is going to be from here to here. So if we can compare the magnitudes of those two values, that's shown here, that the activation energy of the enzyme catalyzed reaction, delta G ES double dagger, is less than the delta S double dagger of the uncatalyzed reaction. This is the rate enhancement provided by the enzyme on the substrate. So this is the thermodynamic perspective of looking at rate enhancement, lowering the activation energy through enzyme substrate binding. We'll look at the chemical details on some of these enzymes, but that's not the focus here. Understand the concept of lowering the activation energy through enzyme substrate interactions that are not possible with the uncatalyzed reaction. Now we're going to look at enzyme kinetic measurements in which we determine specific rate constants for enzyme catalyzed reactions. Recall our system where we have enzyme plus substrate goes to the enzyme substrate complex, and that complex can either dissociate away or it can move forward through a chemical reaction and form enzyme plus product. We also have the possibility of the reaction being reversible, an enzyme binding product to form the ES complex, kind of reversing the chemical step. There's different rate constants here, right? K1, K minus 1, K2, K minus 2. How do we measure these rate constants? Well, there's ways to do that, and I'm going to go show you a way to do that today in this topic. However, before we get into that, let's think about how do we measure rate constants for chemical reactions in general. So if we just had S going to P, as shown here on this reaction plot, we have time in the x-axis, concentration of P in the y on the y-axis. So imagine if S was converted to P, say P had a double bond that we can monitor spectroscopically. We can follow the formation of P given a certain amount of S over time. So we would start off, say S is equal to 0.5 molar, and the reaction starts, and at time 0 there's no product, and then as the reaction begins, we see these types of curves being generated, that we have a initial linear formation of product, and then it starts to deviate from linearity and kind of levels off over time. If we do and double the concentration, we see that the initial velocity doubles, but then it starts to level off, and so on. And so what we can do is we can define what we call an initial velocity, in which we look at this linear portion down here, where this time course is linear, and then we can determine an initial velocity. And so this initial velocity can be explained in terms of the forward rate constant K. That would be K1, for example, if S went to P, times the initial concentration of your substrate concentration, S. That would be your initial velocity. So K doesn't change, but S does over time. And because you have less S here than you do here, your velocity will go down. And so you see a change in your velocity. So that's why we want to measure the initial velocity when S is the highest concentration that we have. And so this gives us this V0 value here. K is not going to change. That's a constant of the chemical reaction. Okay? So if we were to plot the concentration of these S's here, initial concentrations of S's, versus the determined experimentally initial velocities of these linear regions, and plot that as a function of concentration of S, we would get a straight line, and the slope of this line would be your rate constant K. So that's how you get the rate constant K of this S to P conversion without enzyme, is to do these time courses at various concentrations of S, plot those and get those initial velocities, plot those S concentrations as a function or initial velocity, and then you will get a straight line, and you can get K from the straight line, because you're basically plotting V0 versus S, and so based on this, your slope is K, right? So this linear expression is plotted in B, all right? So this is non-enzyme catalyzed reaction. This is just converting S to P. Now if we add an enzyme, we can look at the same thing at a given substrate concentration as we add more E, because we have a E plus S reaction giving us a velocity, an initial velocity. We have the same type of plot, in that we're looking at the reaction over time as we add E. So you can imagine that you have time 0, you have your substrate in there, but there's no enzyme. You add some enzyme and the reaction goes. You'll have an initial linear burst of velocity, and then it'll level off as substrate is depleted, just like we saw in the uncatalyzed reaction. If we add 2 units of the enzyme, we should see a doubling of the initial velocity, and it will level off in a similar fashion we've seen in the non-substrate or non-enzymatic catalyzed reaction. So we have these time courses here, and we want to make sure that it's linear as well. The more enzyme we add, the initial velocity should increase over time, and indeed that's the case. So when you're experimentally setting up these enzymatic assays, you want to make sure that you're in a range at a given substrate concentration, that your enzyme is behaving as you add more in a linear fashion. Otherwise, something's not right with your assay. So it makes sense, right? The more enzyme you would add, you'd have a larger initial velocity, and it should be linear, just like shown in the other example, okay? So how do we get these other rate constants for these reactions? Because we need to characterize the binding event and the catalytic rate constant as well. So Michaelis and Menton are the two that basically came up with a way to do enzyme catalyzed reactions and characterizing their properties and kinetic parameters. And so they made an important contribution to the field of enzymology, and it's reflected in the Michaelis-Menten equation, which is shown here. So we have our initial velocity that we talked about, that initial burst of the linear portion at early time points, given a concentration of substrate and a concentration of enzyme, and it's related to the following expression shown here. So the Michaelis-Menten equation, you should know this. The initial velocity v sub 0 equals v sub max, we'll define these things later, times the concentration of S over Km, what's called the Michaelis constant, plus S, right? So this V max and Km value help to identify enzymatic catalytic properties, these rate constants that we would see in K1, K minus 1, K2, K minus 2 are contained in these Vmax value and Km value, okay? So if we were to plot V0 versus substrate concentration, we would get a plot looking like this. So again, for every S concentration we have initially in the reaction that we use to get that V0, we would plot that. So it's no different than the plots I was showing before, but instead of getting a linear plot that we saw, we get these hyperbolic functions here. So this is a hyperbolic curve. And so when we are at low S concentrations, these reactions and these initial velocities are more on what we call the first order in terms of the reaction. And then when S gets very high, it becomes zero order with respect to S, that we can add more S, but the reaction really doesn't go much faster. The initial velocity kind of levels off. You can see how it's leveling off here. Here, the initial velocity is going up as we add more S, but eventually the initial velocity levels off because it doesn't matter how much S we have, we can't get any faster. And that's simply because the more S we have, the more ES complex we form. But there comes a limit where you just basically have all of your E into what's called the ES complex. And so if you add more S, you can't get any more ES complex. And so you reach a theoretical limit, and that's related to this dotted line here, V max. But we'll go into a little bit more about that in some other slides. But this is the Michaelis-Menten equation, and this is what you get as a Michaelis-Menten plot. If we were to look at where V max and Km are on these plots, this is better shown in this diagram here, this plot. The V max is this dotted line up here. That's your theoretical maximum velocity. If you have S be very large, you eventually get to V max. So recall the hyperbolic function. We've seen this for our binding curve, where we have a function of x equals ax over the numerator divided by b plus x. X here in this hyperbolic function is S, substrate concentration. F of x is V0. And so all the same parameters apply to these hyperbolic functions. There's an asymptote. In this case, it's going to be A would be our V max, okay? In our binding equation, it was 1, remember? Because we had y between 0 and 1. V max here is going to be whatever A is in this equation. So that's going to be our V max. And we have this hyperbolic curve. And at half the maximal velocity, if we were to find that point here on the y-axis, extrapolate to the curve and drop down, that value would be our B or our Km. So here's how you get the information from the plot. So you can extrapolate out to see what your Vmax is in terms of where your curve is leveling. Okay, so that's going to be your Vmax. If you were estimating it here, you may estimate it to be a little lower than that, you know, so there'll be some error there. But wherever you define what Vmax, you cut it in half, extrapolate to your line, drop it down, and that's going to be your Km value. So Km is substrate concentration at 1/2 Vmax. And Vmax is as fast as the reaction can go if the substrate concentration was infinity. In other words, this line never intersects Vmax, but if it goes to infinity, it would reach it. So your Vmax is the fastest you can go with as much substrate as you can provide. And the Km is the substrate concentration at which you have maximal velocity. These are important parameters, this Km and Vmax from the Michaelis-Menten plot and related to the Michaelis-Menten equation, which is a hyperbolic curve. So Michaelis-Menten pioneers in the field of enzymology, and Maud Menten was one of the pioneers of women in science and biochemistry in general at the time. And so there's a very few opportunities for women back in those days to be in science, and to let alone be recognized for their contributions. But she has been recognized and was a valuable contributor to the field of enzymology. So let's look a little more detail here to try to make this a little more understandable. It takes a while to figure this out. It would be helpful to look at your textbook and read that section on enzymology there, doing some of the tutorials and some of the mastering problems, and thinking about this, because it takes a while to get a good handle on it. So I'm going to try to provide some of that here in these slides. So if we look at our condition here of our situation in terms of the enzymatic reaction of E plus S, I'm going to simplify it a little bit because this is what the conditions are going to be for most of the time for the single substrate reaction, where we have E plus S goes to the ES complex or can dissociate away. So we still have K1, K minus 1. But we're going to simplify the conversion of ES to product by just putting one line here, because the K2 is going to be, K minus 2 is going to be considered very small. And we're not going to call it K2 here, but you can think of it that way. We're going to call it something special called Kcat, the catalyzed reaction. And so we're going to call that Kcat. And that's going to be the chemical step to form enzyme and product. I just left the E out of here, but it would still be here because E just is over here now binding to the substrate again. You generate E again. All right, now if we were to plot these different concentrations of these components over time, what would it look like? Well, let's look down here at our time course. This is 0, okay? Here are our concentrations. So say we can measure everything, not just product. So if we did product and look at product formation, you see your product here goes up over time and starts to level off. If we were monitoring S, see at 0, we have 0 product, it's all S. And so as S gets converted to P through the enzyme catalyzed reaction, we see S go down. And then, of course, we see P go up. All right? So that would make sense. We have to start the reaction with some amount of E. And so that's going to be here. Whatever this concentration is our E sub 0, or initial E concentration, or E total, because that's what we would have in the cuvette to do the assay. So the enzyme concentration doesn't change as a catalyst. It's not going to be consumed in the reaction. It'll be used, but it'll be regenerated. So it's going to stay the same concentration. However, its form may be different. So we have two forms of the enzyme. It's either going to be the free E form or the ES form. And so we can monitor these two forms. So when we first start the reaction, there is no E and S combining initially. So we have 0 of the ES form, and everything of E, free E, is all the enzyme by itself. Once we have the reaction start, E starts to form with S to go to the ES complex. So we see a rise in the ES complex over time. We see a corresponding decrease in the free enzyme concentration over time because it's being bound by S. Okay, S is going down, product starts to form as well, because as ES forms, it can either dissociate away or go back. And so we see E initially go down, free E, because it's all 100% free at time 0. And then we start the reaction, it gets starts to bind, so free E goes down, and ES goes up. Notice the curve of ES goes up, and then it kind of goes down a little bit and kind of levels off. There's not really much of a change here in the E concentration of ES over E. We reach what we call a steady state. In other words, the concentration of ES over time is 0. We don't see a change in its conversion. It's kind of like these, it gets to a point where it's forming, it's going over here, but then it's forming, it's going back. So you get to a point, it's not an equilibrium now, because it's a dynamic thing going. Equilibrium means the forward rate and the reverse rate are equal. That's not what's happening here. But what's happening is it's this concentration, and these rate constants are such that its concentration here is not really changing very much over time as you're making product and converting substrates to products. The ES form is kind of like at a concentration, it's not changing over time. It's a steady state, okay? That happens after a certain period of time. If you study these initial earlier time points where ES is rapidly increasing and E is rapidly decreasing, that's called pre-steady state. So pre-steady state is looking at the formation of the ES complex. So if I wanted to get some of this K1 and K-1 values here, I would have to study enzymatic reactions in this area, okay? If I want this K-cat, I'm looking at studying in the steady state area. So that's what we're going to focus on, is the steady state, because we're looking at the catalytic rate enhancement of this reaction. We can get these binding constants in a different measurement, but what we're going to do is be looking at what we call steady state kinetics. We're going to be looking at this point where the concentration of ES over time does not change. Okay? So in doing our reaction, understand the pre-steady state versus the steady state condition, okay? And the following assumptions, that when we have to, in order for this to occur properly, we must have the substrate concentration be much greater than the enzyme concentration. We can make that, because we can experimentally do that in our cuvette. But this is usually going to be the case because an enzyme is a catalyst. You don't need much to get it going, because it's used, but then it's regenerated in the process. So it keeps being used over and over again. You don't need much of it. You just need a little bit to get it started. Hence the definition of a catalyst. So this has to be true. And then we must also be able to have the condition and where the change in ES over time, the differential here, is 0. It's not changing very much. So we have to provide conditions in order for this to occur. And so that's what we mean by steady state concentrations. So some of the problem sets have some data for you to plot that were generated based on these initial velocities and substrate concentrations to generate your own Michaelis-Menten plots. But this is some of the things you have to consider in terms of enzymology, how to measure these rate constants, and we're going to focus on the steady state enzyme kinetics here in this course. So I still haven't shown you how to calculate Vmax and Km, other than if you already have a plot, you can extrapolate those values out. But how is this related to what I showed in the previous slide? Well, Vmax is the maximal velocity, how fast the reaction can go. And so that's going to be equal to the Kcat times the enzyme concentration. So the more enzyme you have, the faster the Vmax will be, because the S's are going to be always going to be concentrated in such a way that they're much larger than the enzyme concentration. So the enzyme total is going to be related to the Vmax. Okay, the more enzyme you have, the Vmax is going to be greater. This is kind of what I showed in the few slides ago, where if you double the enzyme concentration, you double the initial velocity. You double the enzyme concentration, you're going to double the Vmax. And the proportionality constant here is the catalytic step kcat. So there's your kcat. We're looking at the maximal velocity that's possible, kcat times E total, because the E total is going to tell you how fast that reaction is going because we're at saturating S. S concentrations of S are so high, you can't make the reaction go any faster, but if you add a little more enzyme, you will. So Vmax equals kcat times E total. And so we can calculate kcat by knowing what the Vmax is and dividing by how much enzyme we have, because we know how much enzyme we have because we experimentally put it in there. So we can calculate kcat. So that's how we can get kcat information. So now we have a kcat. From the Cayless-Menten plot, we get Km. But you can derive the microscopic rate constants of the expression that we had previously, with K1 being the formation of E plus S, and K minus 1 being the dissociation of ES to E plus P, and then K2, or in this case kcat, going from ES to E plus P. And you could derive Km, and that's shown here, that the Km is the addition of K2 and K minus 1 over K1. And since the value of K2 is small, usually, it can be approximated to be K minus 1 or K1. So one is tempted to think of the Km value as a dissociation constant, because they're looking at the rate constants of the reverse reaction over the rate divided by the rate constant of the forward reaction. In other words, the dissociation of substrate from the enzyme is related to K minus 1 in the dissociation reaction, and the association of E plus S to form the ES complex in the forward direction is related to the forward rate constant K1. So the ratio of that would be your KD. We talked about that before when we looked at equilibrium constants at the other topics earlier in week 1. However, if you look at Km, you'd say, oh, it's going to be a dissociation constant, but it's not, because it still has contributions of K2. So although numerically it would be a very similar number because K2 is going to be small, usually relative to K1, the dissociation rate is usually going to be, rate constant is going to be larger than the chemical rate constant. It's really not a KD. You can't use that to say that's the KD of enzyme and substrate binding. I like to think of it, it's just the substrate concentration at 1/2 Vmax. That's exactly what it is. So you can see it's a complex combination of rate constants here, okay? So Km is not the KD, but the substrate concentration in which you are at max, half maximal velocity, all right? So the two key parameters to determine the strength of an enzyme is the kcat and the kcat value divided by the Km value, all right? So let's look at the first one, the kcat value. The kcat value is called the turnover number and indicates how fast the enzyme can work under the conditions where there is saturating amount of substrate, and the better the enzyme, the larger the kcat. Basically, you're looking at the reaction of ES complex to form enzyme and product. So basically, you're looking at that catalytic step, that chemical step. So the larger that value is, the better that enzyme is in converting the substrate to the product. and you're turning over the enzyme because the enzyme is going from the ES form to the E plus P form. Now there's free enzyme, and so it can go back and bind another substrate molecule. So that's why we call it turnover number. And the units of that is going to be inverse seconds. And so that's the turnover number, kcat. All right. In terms of enzymes' ability, the more efficient enzymes will have a small value of the Km. In other words, if the Km value is small, that means you don't need much substrate to be at 1/2 Vmax. Okay, so the Km value is important too for an enzyme, for a substrate. So we would like to have a large kcat and a small Km for the enzyme to be efficient. So the most efficient enzymes have a large kcat and a small Km. All right? Now we can also look at an enzyme catalyzed reaction in which substrate concentrations are very low. They're well below the Km. Remember, if they equal the Km, they're 1/2 Vmax. But let's go lower than that. Let's go to 1/100th of the Km, for example. So we can extrapolate the reaction as such that the substrate concentrations are so low that we can think about the reaction in terms of the association of E and S as the initial velocity, because we just don't have a lot of substrate to build up a lot of ES right away in terms of the concentration of it being low. So we can think of it as an initial velocity is kcat over Km times E plus S. So this is now a second order rate constant, this kcat over Km. And so we call this particular expression, kcat over Km, the enzymatic rate constant or the catalytic efficiency constant, because it measures the overall efficiency of the enzyme, because it combines the catalytic step as well as the substrate recognition step. So like I said, if you have a large kcat and a small Km, you're going to get a big value for kcat over Km. And that's going to be a more efficient enzyme. So efficient enzymes have large kcats and small Kms. Let's look at a table of data here for various enzymes and see what kind of information you can obtain. So this is what the bottom line is. I want you to be able to understand what these values mean and how to rank enzymes based on these values. Is it an efficient enzyme or not? And so here is a list of enzymes and their substrates and the calculated or experimentally determined kcat. That's going to be usually inverse seconds. Okay, it could be inverse minutes, just depends on the enzyme, but it's usually going to be inverse seconds. The Km value is going to be your substrate concentration at half maximal velocity. In this case, it's listed as molar, could be millimolar or micromolar, just depends on the data that's presented. And then you have your kcat over Km, which is your second order rate constant. In this case, it's going to be inverse molar, inverse seconds, because when you multiply by molar versus molar, concentration of E times the concentration of S, one of your molar concentrations will cancel out and you get molar per second, which is going to be your velocity. Molar per second, concentration per second. So that's your second order rate constant, your catalytic efficiency or enzymatic rate constant. Okay, so let's look at some of these values. So if you look at these kcats, you can see they vary. Here's a 10 to the minus 2, to the minus 3, to the minus 7. Wow, that's very large. That has a high turnover number, this catalase. So it's very, very good at turning over. Once you get ES formed, it's going to form EM plus P. That's what that's telling you. 1,000 times better than, or 200 times better than this guy. Carbonic anhydrase using bicarbonate as a substrate. Okay, let's go to Km. which enzyme is able to catalyze, get 1/2 Vmax with the lowest substrate concentration. We want the Km with the smallest value. And so 5 times 10 to the minus 6, that's the smallest value in the table. And so that's going to be the one that has the substrate concentration, lowest substrate concentration to hit 1/2 Vmax. And that's in the case of using fumarate as the substrate. All right. And now we look at the catalytic efficiency, Kcat over Km. So we have one that has the highest Kcat here, catalase, one that has the lowest Km here, but which one is the overall more efficient? Is it going to be one of these two or somebody else? So you want to look at the largest number you can get here in this table of data, or this column of data. And so if you look at this one, you would want to see what's the largest value here. 7, 7, 8. Ooh, there's a couple 8s here. And we got to look at the coefficient. Ooh, 2.8. This one is the most efficient. So it's crotonase. So crotonase didn't have the largest Kcat. It didn't have the lowest Km, but the combination allowed it to be the most catalytically efficient. Okay, and so that's what happens in enzymes, is that you have to utilize the enzyme for binding of the substrate, and have the enzyme catalyze the reaction. So if you put more emphasis on binding, you have less binding energy and interactions to promote the catalysis, lowering of the transition state. If you put more emphasis in your design of the enzyme to bind the transition state and lower the activation energy, you may alter substrate binding a little bit, and so it's going to affect your Km value, because that's the substrate concentration at 1/2 Vmax. So if you kind of tweak it just right, you can get the most efficient enzyme, but it may not have the largest Kcat value or the smallest Km value. This is the stuff that I want you to think about in terms of these values and what they mean. All right. Now, in terms of theoretical limit, how fast can a enzymatic reaction go? Notice that the ones that are on the top are 10 to the 8th, and they kind of hover there pretty much the same. And that's because how fast can you bring two things together in aqueous solution? And if they were just to diffuse together, well, the diffusion constant is around 10 to the 8th inverse molar inverse seconds. And so you can't really usually get any higher than that. You can go to maybe 10 to the 9 if, say, the molecule was charged and it was able to come together more efficiently in some way. But this is your theoretical limit, 10 to the 8 or 10 to the 9. You can't get any faster than just bringing two things together, because once they come together, binds to the active site, then rotational degrees of freedom change, and the enzyme will promote the binding to in such a way to allow the catalytic process, the chemical process, to occur. So how fast can you bring two things together in solution, 10 to the 8th or 10 to the 9th? That's going to be your most efficient enzymes. The chemical step has been delegated by the enzyme in such a way, it's so efficient that you're limited by how fast two things can come together. You're just limited by the diffusion of two things coming together in solution. It's not the chemistry anymore. It's not the chemistry anymore. So that's how efficient enzymes can be, that the chemical process that would take thousands of degrees to do something in a non-enzymatically catalyzed way has been taken care of by the enzyme, such that we're limited by diffusion, how fast two things come together in solution. That's very efficient. Those are your most efficient enzymes. In this table, there's some very efficient enzymes here. So how do we determine the Km and Vmax values, or these Kcat values, from Michaelis-Menten plots? So here's our plot of the Michaelis-Menten plot at different substrate concentrations, okay? And for the Michaelis-Menten equation, we're going to expand it out a little bit here. So it's initial velocity equals k cat times E total, um, and the concentration of S over Km plus S. So instead of V max, I got k cat plus E total here. So there should be E total here for E. It's not the free E. So sometimes we'll abbreviate it as just E, but it should be E total here, so you understand that as well. So this is the concentration of the initial or enzyme total that's present. Okay, it's also here for S as well as the total. It's what we have in our reaction at these different concentrations when we start the reaction. Okay, so this is the expanded Michaelis-Menten equation, and we can use two regions of this plot. The first region would be this first order component down here in terms of with respect to S. These early lower concentrations of S, we can determine the k cat over Km, because recall that when we're at low substrate concentrations and the Ks is less than the Km, the reaction is dependent upon both the enzyme concentration and substrate concentration. So we have this second order equation of k cat over Km times E plus S. And so that's basically going to be linear. If you zoom in on it, that looks more like a straight line. And so we can use that linear part to obtain this equation basically here, that the enzyme reaction is based on first order with E and S times a proportionality constant, which is k cat over Km. So we can determine k cat over Km from this initial linear slope, because this becomes y equals mx plus b, x being a combination of E and S. And so if we get the slope of this linear part, we have k cat over Km. So that would be the slope. All right, if we're at high concentrations of S, we're saturating, and the reaction becomes zero order with respect to S. So our initial velocity reaction is just based on enzyme amount. And so it becomes V0 equals k cat times E, and because everything's in the ES form, so it doesn't matter if we add more S, it's not changing anything. And so the reaction is broken down in terms of it's dependent upon E, and we can calculate k cat because we know how much E we added. And so, and we know the initial velocity, and so we can calculate k cat. And so we have k cat, and if we have k cat over Km, we can calculate Km. And so that's how you can determine this from estimates from the Michaelis-Menten plot. Initial velocity, a linear portion here, define k cat over Km, and then looking at what the V max is for this value, extrapolating that to determine k cat based on the enzyme concentration that we started off with. And then those two values can be used to determine the Km. Or you can easily go at the half V max and drop it down. That's another way to do it as well. Okay? So understand how to get k cat, Km, k cat over Km from these plots. Today we have curve fitting software that will fit any kind of equation in terms of a function to fit a curve based on data. It can be a polynomial or higher order polynomial or something like that. No problems in fitting hyperbolic functions. And so from the curve fitting of the data you provide, a k cat and Km can be calculated for you. But back in the day before, 50, 60 years ago, when people started to do a lot in enzymology in the late 50s and early 60s, it was hard to get good estimates from these plots by hand, despite the best efforts. So there are ways to transform hyperbolic functions into linear functions, and we'll talk about that in what's called the Lineweaver-Burke plots. And I'll show you kind of how that has been developed over time as well. But right now, if looking at these curves, understand the key parts of the data related to k cat, Km, and k cat over Km. I'm going to emphasize it again in some other slides as well. But this is kind of a summary slide here of where we're going to go from. So let's look at another plot and thinking about it again. So you have E plus S forms the ES complex. K sub 1 forward rate constant. K sub minus 1 reverse rate constant of this dissociation of E and S. And then the catalytic step K-cat to form product, the turnover number. If we were to write our Michaelis-Menten expression out, we have that here. I kept it as Vmax, all right? So if we were to plot these data, you would have the hyperbolic function here. Here's your Vmax, and this is your initial velocity V0. Sometimes it'll be V0, sometimes it may be V sub I, okay? It depends on the book. You have Vmax over 2. You extrapolate down, that's your Km. Here's your substrate concentration. So there you go. There is your Vmax. There's your Km. You got V over K. You're all set to go. Know your enzyme concentration, get Kcat. So that's how you can get your data from that. And this part down here, initial substrate concentration is very low relative to the Km, is linear. And that's your initial rate. And that's related to your Kcat over Km. All right, so just remember, Km is the concentration of S when half the enzyme total is bound. In other words, your half Vmax. And Vmax is the maximum reaction rate, theoretical limit. Occurs when all enzyme is bound, so the Vmax equals Kcat times E total. So you want Kcat, find Vmax, know how much enzyme you started with, and you can get Kcat. You want Km, know what Vmax is, cut it in half, look at your curve, drop it down, you got your Km, all right? As mentioned before, that there were some issues in getting some of these values from these hyperbolic plots to do those in a non-linear regression fashion. In other words, to do non-linear regression analysis by hand is quite cumbersome. So researchers 50, 60 years ago decide, well, let's make linear plots that were mathematical transformations of these hyperbolic functions and use linear plots to help us determine Kcat, Km, Vmax from linear plots, because linear regression is easier to do than nonlinear regression analysis. And so I'm just going to show one of these and transformations called Lineweaver-Burke, and this is important not only historically, but also when we look at enzyme inhibition, because Lineweaver-Burke plots give you characteristic features that you can tell what kind of inhibition you have. So it's also a way for you to get Kcat, Vm, Vmax, and Km from a linear plot. And most of you have Excel, so that works very well for linear regression. It's not good for nonlinear regression analysis. And so it's a way for you to analyze kinetic data. And so I provided in the problem sets kinetic data for you to analyze. And the best way to do it is to convert them into Lineweaver-Burke plots to get your Cat, Km, and Vm values. Okay, so sometimes I'll say Vmax, sometimes I'll say Vm. It just depends. You'll see that being used in different presentations of enzymology. Also, Kcat over Km is sometimes will be referred to as V over K, because Vmax has Kcat in it, and so often we'll use the V over K value there for that catalytic efficiency constant. So just kind of keep that in mind if you start looking at some of the other literature out there, or watching some other videos or something like that. It's still the same thing. It's just a different way to express it. And just a little distinctions there, but it's still telling you the same thing. V over K is the second order rate constant, like Kcat over Km, and that the Vm or Vmax is the same thing as well. Okay, it's just a different abbreviation. So if we take the Michaelis-Menten equation and we flip it, we do a double reciprocal. We put 1 over V0 over Km plus S over Vm plus S. And you can do this yourself. I'm not going to spend time doing the derivation. You end up with this linear expression, which is 1 over V0, that's your Y, equals M, which is going to be your Km over V max, X, in this case is 1 over S, plus B, 1 over V max. So that's shown over here on the right. This is your Lineweaver-Burke linear transformation of the hyperbolic Michaelis-Menten equation. And you have a linear plot now. Your slope is going to be Km over V max. Your y-intercept is 1 over V max. And your x-intercept would be where x is 0, or 1 over S is 0, I should say. And then your, I'm sorry, x is 0 is here, so if x is 0 here, 1 over S is 0, so that's your V max. When y is 0, then you can solve for 1 over S, and you will see that it becomes 1 over Km negative. And so this is your Lineweaver-Burke plot. And so if you plot 1 over the concentration of S over the 1 over your initial velocity, your data points will all be in this area, and there'll be a couple points here, but the spacing will be different. So you saw the nice even spacing in the Michaelis-Menten plots. These will space out differently because you're dividing by S. So the smaller the value of S, the bigger 1 over S will be. And so you'll have your values here won't change very much because S's are very similar. And when it gets smaller, this number gets much larger. And so you have an unequal distribution of 1 over S values unless you started and figured out what your 1 over S values were going to be in a Lineweaver-Burke plot. Then you can convert them back to a concentration of S. So that was more experimental details there. And you probably want to know, but there's ways to make the spacing even if you're to look at the data to get better estimates of Vmax and Km. So from these plots, you should be able to also recognize what they are, 1 over V0 over 1 over S. It's a linear plot, and you can get Vmax and Km based on these y and x intercepts. And also the slope, you can get Km over Vmax. So me, I like using the Vmax here for the y-intercept and getting the slope, and then from the slope and the Vmax, calculate Km from the slope and Vmax, as opposed to the x-intercept, okay? Because the values will be a little different, okay? But the best aspect of this is that you can at least get some parameters for yourself from the data if you just can only do linear regression. And they should be very close to the values you get from the Michaelis-Menten plots if you did them by eye. But it'll be better because you're extrapolating here to saturating substrate, where S is going to be infinity, that's going to be 0. And so that's going to be your asymptotically limit, asymptote Vmax. Okay, so it's just a linear transformation of that hyperbolic function. So what happens when we add allosteric effectors? Remember, allosteric effectors bind to the enzyme somewhere that affect its behavior. We saw that with hemoglobin. There's 4 allosteric effectors there, and we saw how when these allosteric effectors were bound to hemoglobin, it affected its ability to bind oxygen. Well, the same thing can be true for enzymes. If it's a dimer or a tetramer or a hexamer, allosteric effectors can, even a monomer, can affect its regulation. So small molecules binding to enzymes, not at the active site, but some other site, some interface between the multimeric unit or the monomer itself, will cause the substrates to bind differently, the enzyme to catalyze the reaction differently to promote the chemical step. And so you have 2 versions of these allosteric effectors. One is an activator that is a ligand that increases the activity of the enzyme, and so you see a change in your Michaelis-Menten plots, okay? So with the activator, things go faster, and the allosteric inhibitor decreases the enzyme activity, so things go slower. So let's look at this plot here of Michaelis-Menten data. Enzyme by itself with no activator or inhibitor, no allosteric effector. You see here that, hey, this is not hyperbolic. It's got some sigmoidal action. So yes, it does. And so there is an evidence for this being some kind of a multimeric enzyme, that the binding of the substrate affects binding of other substrates to the other subunits of the enzyme. And so you're seeing this positive cooperativity being displayed. So that's very possible. We saw this with hemoglobin, right? This ability of oxygen to bind changes its ability to bind oxygen. The first molecule is hard to bind, the second one is easier, the third one's easier, the fourth one's easier. You have this little sigmoidal action. But when you add an allosteric effector, you can have it more pronounced. You can have it more sigmoidal. And that's what we're seeing here. When we have a inhibitor, it's making the binding of the substrate even more difficult. And so we have more sigmoidal behavior. And notice the initial velocities aren't as high at given substrate concentrations because it's more difficult for the enzyme to catalyze the reaction. Okay? If we have an activator, it may allow the enzyme to bind the substrate so efficiently that we lose its cooperativity altogether, and it's purely a hyperbolic function. So it's even more active. You're having less restriction on the enzyme's binding of substrate to be required to promote the reaction. The activator kind of changes the conformation of the enzyme that allows it to be more efficient. And so a good way to think about that, even though they all have the same Vmax, is to look at the Km value, the value of the substrate in which your half maximal velocity. So if we look at the half maximal velocity and extrapolate across these curves, here's the Km that is the substrate concentration for 1/2 Vmax for the enzyme without any allosteric effector. If we add an activator and making it more efficient, a faster enzyme, it is a more efficient enzyme, I should say, the substrate concentration requirements will be less, and the Km is lower. So we call it a Km apparent. The Km has changed for the substrate based on the presence of an activator. So we need less substrate to get at half Vmax than we would without the activator being present. So the enzyme now is more efficient. If we have an inhibitor, then it takes more substrate concentration to get to 1/2 Vmax, and so we have a new Km apparent, and we identify the allosteric effector as an allosteric inhibitor because it slows down the reaction. We need more substrate to get 1/2 Vmax, so the enzyme is not efficient. So you will see this in play quite a bit with metabolic pathways that we'll be discussing in other topics, that there's a series of activators and inhibitors that control these enzymes. Not just one or two, but there could be 5 or 6 different activators or inhibitors. You may have 1 activator and 6 inhibitors that function on that particular enzyme that regulate its ability to catalyze the reaction. And so that's the hallmark of biochemistry, this regulation of enzyme activity based on metabolites binding to these enzymes and changing their enzymatic properties, slowing down or enhancing chemical reactions based on need, based on what's needed by the cell. So to me, this is the part that got me interested in biochemistry as a student, and I ended up pursuing that in my graduate studies in terms of being studying enzymology and protein binding interactions and methods to look at how things are recognized and ways to characterize proteins in their dynamics in solution. So I know that was a lot of information, and you may be overwhelmed at this point, at this process of the presentation, but believe me, it can get a lot more complicated. And I just wanted to show you the complexity. You're not going to be required to know any of this stuff, but I just wanted to show you that most enzyme reactions require two substrates, not just one. And so in this case, we call the substrates A, B, instead of S sub 1 or S sub 2. So E plus A would be like your first substrate binding to form the EA complex. And then if you had another substrate that would have to bind to the EA complex to form EAB. Okay, now you have your two substrate bound to the enzyme. Now you go to do your chemical step, and now you have products P and Q, okay, two products now. And then you can dissociate the products one at a time. So maybe P comes off first, and then you have EQ complex, and then Q comes off, and eventually you get to E. So you can see the complexity now has risen quite a bit, because you have two binding events, a chemical step, and two product release events. So each one of these has a rate constant, K1, K minus 1, K2, K minus 2, K3, K minus 3, K4, K5. Okay? And so there's ways to derive steady state reactions for initial velocity plots based on the enzymatic mechanism of product binding and release. And that's what's related to these different names. And so if we say ordered sequential by, that would indicate that you have two products and two reactants, by, two products, by, two reactants, by, two products, by. And it's ordered that A must bind first, then B. If it were random, it doesn't matter which one binds first, A or B. B can bind first to form EB, then A combined, or A combined to form EA, then B combined. So it'd be a random binding, okay? And so you end up with steady state equations that look like Michaelis-Menten equation, but more complex, right? There's a Vmax here, okay? But since you have two substrates now, instead of S, you have A times B. Then you have KAs and KBs, and there's different types. And so we have a lot more Michaelis constants here, and we have all possible terms. Instead of just S in the denominator Km, we have the product of A times B, and then B times the Km of A, then A times the Km of B, and then this complex here, or this constant here, of two different types of Michaelis constants, an inhibitory A and a Km of B. And if we have random, you can see it gets a little more complicated in this constant based on the model. All right. And another one called the ping pong mechanism, and that's actually what serine proteases are, but because B in the case of serine proteases is water, anything with B will get dropped off, and so we end up with the single substrate model that we talked about exclusively here in this topic. Okay, so I just wanted you to notice that it can get quite complicated when you have two substrates, but we're not going to go there. If you were to be a biochemistry major, and you will then encounter this in one of your major courses as a senior, your last biochemistry course. But since you're not biochemistry majors, we are not going to go into this. But I just wanted you to be aware of it. It's still the same thing, except it's more complicated because you got more of these events, and so your equations just get bigger. The analysis is a little different, but the concepts remain the same. It's still steady state kinetics. So another way to look at enzymatic reaction with two substrates and to have a feel for if it's sequential or ordered is to look at these linear diagrams called Cleland diagrams. And so the linear expression I showed before, it's hard to keep in mind if it's sequential or if it's random. You have no idea, unless I would have to rewrite it quite a bit. But this was a way to abbreviate it in a way that you can kind of think about the substrate coming in and binding to the enzyme, and we're looking at the reaction going from left to right, and products being released with the arrow going up, substrate binding with the arrow going down. These are called Cleland diagrams. So here's an ordered situation, and then here is a random situation. So you can see E can bind either A or B, and then B comes down. So you can see the complexity in this diagram, and that's reflected in the derived steady state equations on the previous slide. And so you can see you have more events, and so your equation is a little more complicated. The ping pong mechanism, which is what serine proteases undergo, the enzyme does change its form from an E form to an F form, and that's because it's a covalent modification on the enzyme, and so it's been converted to a different enzyme form. But notice eventually that you end up with your free enzyme at the end. So you always have that because it is a catalyst and it is regenerated. So these diagrams are helpful in trying to figure out the type of mechanism you have, and then figuring out the microscopic rate constants for each one of these events can be done, but they're very difficult, sometimes impossible to actually determine. But you can get some of the other more macroscopic rate constants like your KMs for those types of enzymatic reactions that require two substrates. So again, we're not going to go into that, but I just wanted to show you that it can get quite complex. But if you have a good firm understanding of single substrate kinetics, moving to two substrate kinetics isn't that difficult. But you have to get a good understanding of the single substrate kinetics, and that's what we're going to focus on here in our course. And so make sure that you follow the learning objectives for this topic, and it's probably best if you write out what those learning objectives are and provide the information yourself to those learning objectives on a different set of notes, so you can really emphasize the importance of that. I showed some examples here and some other details that may not be necessary for those learning objectives, but it's just to give you more information to make it more understandable. Okay, and the problem sets are also important to work on, as well as the mastering assignments and reading the textbook. So this part of the course is usually the most difficult for the students, just because of the newness of it and understanding some of the concepts of what's happening and the assumptions that we're making. So the best way to do it is to just keep working on the problems will help, and thinking about it. So I'm going to try to emphasize that to you in these topics for this particular section of the course, that it's important to do the problems and think about the enzyme and what it's catalyzing, and what Km means, what Vmax means, and what Kcat over Km is. And so, and how do we get that information from Michaelis-Menten plots and Lineweaver-Burke plots? So it'll be more understandable as you work on the problems and think about this. But this is the topic that's here, that's probably the most difficult of the course. So just keep at it, and it will become more understandable as you work your way through it.